Hello, my name is Harshita and this is your Belmont Math Science Center tutor tip. Sometimes students struggle with stereochemistry and what chirality is. So today I'll give a quick recap of isomers and then move on to describe what chirality means, how to determine it, and how to distinguish between different types of chiral molecules. If you guys are ready, let's get started. So first off, we're going to talk about isomers. Isomers are basically like compounds that have the same chemical or molecular formula, but they differ based on their structure. And there are isomers are of two types. There's constitutional isomers and stereoisomers. Constitutional isomers are isomers that differ by their 2D structure. So if you look at this example over here, both of these compounds have the chemical formula C5H10O, but as you can see, they look very different. The one on the left is in this kind of ring structure, while the other one is in the normal zigzag structure that we see a lot in Oreo. So if you come across compounds like that have the same molecular formula, but then they look very different in 2D, like when drawn in 2D, then it means those are constitutional isomers. Stereoisomers, on the other hand, are isomers that differ based on their 3D structure. So that means they look the exact same in 2D, like when they're drawn in 2D, but then when they're drawn in 3D, they're different. So for the example for that one was this picture over here. So if you drew this picture in 2D, it would basically be like the pentagon that they have, but it would just be like two normal lines sticking out from these two carbons in 2D, and that's how all of these would look. But in 3D, which is how they are drawn over here, you use these little representations called solid wedges and dashed wedges that show you if like that compound is like pointing forward, like towards you, or backwards, away from you. So when drawn out like that, this compound has, well, 3 stereoisomers, and they're all different. So again, if you come across compounds like this that look the same in 2D but then look different in 3D, then those are stereoisomers. And stereoisomers are what we look at when we're talking about chirality and doing all the stuff that we do when dealing with chirality. We're looking for Chiral Centers or doing RS configurations, or we're talking about Enantiomers, Diastereomers, or whatever. So we always draw structures out in their 3D form using these wedges when we're dealing with chirality. So before we dig deep into that, first we should understand what chiral means. So chiral is Greek for hand. This term is used in chemistry to refer to how some compounds cannot be superposed on top of each other when facing the same direction. So I want you to focus on that bolded italicized word same, because that is very crucial, one, and two, it took me a very long time to understand that, and it took my friends a very long time to understand that too. So I just wanted to make sure you guys understood that at the get-go when you're first getting started with dealing with chirality. So basically, what this sentence means is, if you have an object and you take a mirror image of that object, whether that object be like a real life object or a compound or a chemical compound or whatever, you take the mirror image of it and you superimpose the mirror image on top of the original like object, and it fits perfectly, then it's achiral. But if it doesn't fit perfectly, then it's chiral. So chirality is it kind of defines some of the properties that compounds have. So the example that a lot of people talk about, or a lot of professors give, or what textbooks give, is thinking about socks versus gloves, where socks are supposed to be the example for achiral compounds versus gloves, which would be examples for chiral compounds. So just a side note, when when you think about gloves for chiral, I would say it kind of makes more sense, at least to me, if you think about baseball gloves instead of winter gloves, and I'll explain why in a minute. So we're gonna talk about the socks first. So these are two pictures from the textbook, the McGraw-Hill textbook that I'm sure you guys are using for your class. So in this image, we see that the author has like a sock, and they took a mirror image of it. So they have the mirror image and the original image right beside each other. And here is where the object facing the same direction is important. Facing the same direction basically means you cannot flip them. And the reason why I do not like this picture is because it looks like they flipped this sock onto this sock, which is not right. So I just wanted to like kind of better explain this picture in case other people were also getting confused as to why this is supposed to make sense. So I would say if the author kind of rotated this sock around by 90 degrees this way, then the mirror image of it would also have been rotated around in this direction by 90 degrees. So if you could imagine that in your head, you would see that they would look the exact same, and you could like take this mirror image and place it on top of this mirror image without doing any changes to it, and they would fit perfectly, and it would make sense that they were superimposable. And having that sort of representation of this image would also make this image more clear, because again, they have when the author tries to describe chiral molecules, he says, think about your hands. Your hands are chiral. So if you take a mirror image of your left hand, you get your right hand. And if you try to superimpose them on top of each other, like he did over here, you can see that they don't coincide perfectly. And you can do this with your own hands. Like you can try to place them on top of each other, facing the same direction again. So palms up, or you can do both palms down if you want. But they both have to be the same direction. And you can see that they are not superimposable. So that's what it means for something to be chiral. So when they're facing the same direction, they are not superimposable. And when they're facing the same direction and they are not superimposable, they are chiral. But when they're facing the same direction and they are superimposed, and they are superimposable, then they are achiral. Sorry, I blanked for a second. Sorry. So back to the gloves thing. So you can obviously you can think of the socks for achiral and your hands for chiral, if that makes sense to you, and that's enough, and then that's great. That's good. But if you want like some more explanation about the chirality thing, then I know a lot of professors talk about gloves. Like think about gloves. You can wear your socks on either leg, but you can't wear your gloves on either hand, which doesn't make sense when you think about winter gloves, because at least the ones that I have, I can wear my winter gloves on either hand, and it'll be fine. Like I can switch the hand that I wear my gloves on, and it'll be fine. But you can't do that when you have baseball gloves. So baseball gloves are made in a very particular way, so you have to wear your right glove on your right hand and your left glove on your left hand. Sorry. So that's a baseball glove over there that I have a picture of that you can use like for imagining. And I also kind of wanted to show this sort of representation with the baseball glove. So I have that picture copied on a different document over here. So it's the same exact glove, so I just made 2 copies of it, and they're placed right beside each other. So imagine there's a mirror. Oh wait, before that. So they're the exact same gloves, so to prove that, you can see that if I place them on top of each other, you won't even see the difference, because again, they're the exact same thing. But if you imagine that there's a mirror over here, then this would become a mirror image. So now the glove on the right is a mirror image of the glove on the left. And if I try to superimpose them, it doesn't work anymore. And I guess the most obvious indicator that it doesn't work anymore is if you look at this little curly lace structure design over here, it's on the back glove on the left, but on the front glove it's on the right, which is again a clear indicator that they are not coinciding with each other perfectly, which is why they are not achiral, they are chiral. So that's basically what it means for something to be chiral or achiral. And a good thing about chiral and achiral is all chemical compounds are either this or that. Like there is no middle ground, which is really cool because there's very few things in chemistry that do not have exceptions, and this is one of them. And I love it when there's no exceptions because then that means just less things to remember. So when you see a compound and you're told to figure out if it's chiral or achiral, it's either this or that. So you don't need to worry about, oh my gosh, what if it's a pseudo-chiral thing, because that does not exist. So now that we got down with the definitions, we're going to start doing some testing for chirality. So there's two ways you can test for chirality. There's the first method is looking for symmetry, which you can do by either drawing the mirror images of the compound and seeing if it's superimposable, like we did with the baseball glove, or you could see if there's at least one internal plane of symmetry, which just means see if you can draw a line along the middle of the compound in some way so that the compound is split into exact half and both sides kind of look the same. So for example, I'm not going to draw a compound, but I'm going to draw like a letter. So for example, if I had the letter A and I could draw on a computer, that's how letter A would look like. And I'm looking at it and I can see that I could draw a line right through here, and now both sides kind of look like mirror images of each other, right? So that means the letter A is achiral. So you can do the same with the letter B. So let's do this. The interesting thing about the letter B is, so here, let me do the mirror thing here. If I took the mirror image of B, I'm going to try my very best to make this look like a mirror image. And I don't think I've been successful, but I think you guys got it. Like, if you look at the letter B and its mirror image, even without me drawing it perfectly, even if I did draw it perfectly, you can see that it wouldn't actually superimpose on top of each other perfectly, right? But then if I had just done the plane of symmetry thing, then I can see that I can draw a line right through here, and they would look, if I drew the letter B perfectly, or a little better, they would look like the top would look like a mirror image of the bottom. So it doesn't make sense that one test passed and one test failed, right? Well, that's because the mirror image test did not fail. What you can do is you can make slight changes to the compound or object that you're looking at and do that mirror image test again. So I could rotate the letter B a little, and if I drew it out, you would see that now they do look the same, kind of. So now I could theoretically put them on top of each other and have them be superimposed. So yeah, so I just wanted to make that point that you can make some minor changes to a compound if you don't see its symmetry immediately the way it's given. So that's how you would do test 1. And again, if the answer is yes for either condition, that you can either find a plane of symmetry or get the mirror image to be superimposed on top of the original, then the compound is achiral. Otherwise, it's chiral. So that's the first test. And this is a pretty simple, straightforward test, and it's really easy to do with like smaller compounds, but as a compound gets bigger or more complex, like it has more branches or whatever, it gets harder to see symmetry, so you wouldn't be able to see the plane, the internal plane, and it would be really hard to draw out the whole compound and then draw out the whole like all of its mirror image. Like that's just very time consuming. So that's why there's a second test, and that is to see to look for chiral centers, or also called stereogenic centers. So a chiral center is basically a carbon that is bonded to four distinct groups. So it's basically a carbon that has four different groups attached to it. So the way this test works is, if you have a compound and you're looking for chiral centers and you don't find any, so if there's no chiral centers, then the compound is achiral. If there is one chiral center, then the compound is chiral. But if there are two or more chiral centers, then the compound could be either chiral or achiral, and you would need to do further testing to kind of be sure about which one it is. So before we get into learning about that further testing, we need to go through one more thing, and that is determining R and S configurations. So R and S configurations are basically representative of how a chiral center is arranged, and that is important because how it's arranged kind of has an effect on some of its physical properties, like optical activity. So there's a couple of kind of steps that you need to follow to determine the configuration, which is you need to give or assign priority to the four different groups that are surrounding that central carbon of the chiral center, and then you need to draw an arrow from like 1 to 2 to 3, and the direction of that arrow determines whether that chiral center is of R or S configuration. So I'm going to walk you through those steps, and I have them kind of written down over here, and well, all of them are basically rules except the first one, which is more of a tip, because that's something that I do that might be helpful to some of you guys. So the first step is draw the tetrahedral structure of the chiral center. So that basically just means this type of structure over here. So you would have the central carbon of the chiral center over here, and then the four distinct groups pointing out in these four kind of like branches. And I would draw it this way to kind of give myself less chances of confusing myself. So that way I would just need to look at, like, okay, let me rephrase this. I wanted to make sure that I didn't confuse which carbon I was looking at when assigning priority, which will make sense in a minute. So I just drew structures like this. I didn't always actually physically draw it. Sometimes I would just draw it in my head, because after a while I just got used to it, and so I was able to imagine it in my head. But again, whichever works for you, you guys can just keep it in whatever the structure is given. So if it's given in a structure like this, then you can just keep it like that, or if it's in a structure like this, you can keep it like that, or you could draw it out like this. It doesn't matter. It's really just your preference. Anyway, moving on to actual steps. The first step is that the atom connected to the central carbon with the higher atomic number is given higher priority. So this is where we're going to start assigning priority, or going over the rules of how to assign priority. So this one says the atom that has the highest atomic number, or the higher atomic number, is given higher priority. So we're going to look at this one over here first. So we look at this and we see that this is this chiral carbon, and it's attached to a bromine, a hydrogen, and a carbon plus some like extension of the chain, and then another carbon at some extension of that chain. So out of bromine, hydrogen, and carbons, we know that bromine has the highest atomic number. So bromine would have the priority number 1. The second priority would go to the carbons, of course, right? Because carbon has a higher atomic number than hydrogen. But which carbon would you give it to? This one or this one? So that's where the next next step comes in. So if the central carbon is attached to the same atom in more than one of its groups, go to the next atom in the chain and redo the previous test, which is this one, until the tie is broken. So that's what happened over here. We have carbon attached on both sides, so we're going to go to the next one. So this carbon is attached to 2 hydrogens over here and an oxygen in blue. And carbon B here is attached to 1 hydrogen, and then it's double bonded to an O. So if it was single bonded to an O, then we would say it's attached to 1 O, but it's double bonded. So would you count that? Would you still count that as 1, or would you count that as 2? So and the next rule kind of clarifies that. So it says if you come across double or triple bonds while assigning priorities, look at those as if there are 2 or 3 bonds to the atom. So that would mean you would consider this to be attached to 2 oxygens, which is what they have written here. So carbon A is attached to 2 hydrogens and an oxygen, while carbon B is attached to 1 hydrogen and 2 oxygens. So now you would compare to see which one has higher priority. So this one has an O. Oops, my bad. And oh my gosh, I'm gonna draw an H right now. Okay, here, let me put this up here because that thing is coming in the way. There. Sorry guys, it's really hard to draw on a computer. Okay, you know what, maybe we should, there, H. You know what, I'm gonna draw it over here. H, so that's on carbon A. Okay, this will be faster now. And there's an O. Oops, maybe not so faster. O. And an H. So we have 1 oxygen and 2 hydrogens, 2 oxygens and 1 hydrogen, right? So now I look. So there's 1 oxygen over here and 1 oxygen over here. So it's the same thing on both sides. It doesn't really matter. It's not really helping us. Then we have a hydrogen over here and a hydrogen over here. It's also the same thing on both sides, so it's not helping us. So now we're down to an oxygen or a hydrogen. And we know that oxygen has a higher atomic number than hydrogen. So it means this side wins. So carbon B wins. So it gets priority number 2. So that leaves carbon A with priority number 3, and carbon 4, the group 4, group hydrogen with the priority 4. So we got through that. We named all the priorities, right? 1, 2, 3, 4. Now we go to the next step. It says, after assigning priority, always make sure that the lowest priority group is on the dashed wedge, which means the lowest priority group always has to be facing the back of the molecule, okay? And we look and we see that the hydrogen is not facing the back of the molecule. It's on the solid wedge. It's facing the front. It's in the opposite position. So there's a couple of ways that you can get it to be on the back side of the compound, so to be on the dashed wedge. The first method is something that I found confusing when I first learned about it, so I might not explain it so well, but it is that you're supposed to switch whatever's on the wedges. So the BR would come over here and the H would come over here, and then you would switch these two, kind of change, so that this group would come to the left and this group would go to the right. So you would make those changes, and then you would go to the next step, which would be drawing the arrow. So that's one method. The second method is you can just go ahead and draw the arrow and figure out the configuration, and right before you put the answer down, you switch the configuration. So for example, you did the configuration for this one and you got R configuration, then that would mean that the actual configuration is S because the hydrogen is not in the back, and if you would move it to the back, then the configuration changes. And the same with the other way around. So if you did the configuration and you got an S, then that would mean the actual answer is an R. So that's method 2, which is what most people take, and I understand why. It's kind of pretty simple and straightforward, and there's lower chances of getting it wrong. There's a third way, which isn't actually an official way. It's more of what I do, which is actually a little harder than the second one, but it just makes more sense to me. So what I do is I kind of imagine myself holding on to one of these like normal bonds or normal chains, so either group 3 or group 2. So basically not one of the wedges. Well, I would think of holding onto one of these two, like, and hold it up so that the other 3 would be facing down. So kind of like I'm holding a flower upside down, I guess. And then I would kind of twirl the flower, in a sense, until the hydrogen looks like it's in the back, and then I would place it back in this position so that the H would be in this position, and the BR would, again, since I twirled it, it would go to this position over here, and then this group with the double bonded oxygen, since I twirled it, would go around and it would come over here to the solid ridge. And then I would just do the arrow, which is the last step for any of these methods. So, I mean, you could do either one of these 3 steps or 3 methods, whichever one is easier for you. So the last step, which I've been alluding to a lot, is drawing the arrow. So you would draw an arrow from priority group 1 to 2 to 3. If the arrow goes clockwise, the chiral center has an R configuration. But if it is counterclockwise, the chiral center has an S configuration. So I'm going to use the second method for this one because it's easiest to show. You can look over here that if I draw an arrow from 1 to 2, 3, it kind of goes in a clockwise direction. Whoops, not just draw here. Oh, there. It would just go this way in a clockwise direction. So that would mean this is in the R configuration, but remember you have to switch it. So that would mean the actual compound is in the S configuration. So that would mean this one has an S. Here, I'm going to draw that. Oops, my bad. So this is in the S configuration. So we can do an example over here. Since that one already had the numbers labeled, it was like no surprise that it happened that way. But this one doesn't have any numbers, so we can do this one. So we look at which one's the chiral center. So remember, the chiral center is a carbon that's attached to 4 different groups. So let's start from over here. We look at this, and this has 2 hydrogens, so it can't be it, because the hydrogens are the same. Then you go over here, and this one also has 2 hydrogens, and that also cannot be it. You go over here, and you have a hydroxyl group, or an alcohol group, a methyl group, and a group that kind of leads to a carboxylic acid group, and then a group that leads to another alcohol group. So that's 4 different groups. So there's one over here. So there's a chiral center over there. Then we go over here, and there's again 2 hydrogens, so that's not it. And then I can go over here, and well, this one's not even in the tetrahedral structure because it's double bonded to an L, so that's not it. So there's only 1 chiral center here. So we found the chiral center. Great job, guys. So the next step is giving priority. So again, let's look at which one has the highest atomic number. We look at over here, it's attached to an O. Over here, a C and something else. Over here, a C and something else. And over here, a C and something else. So obviously the O has the highest priority. So we'll give it a 1 over here. Oops. And now we get the carbon, carbon, carbon. So we're comparing 3 carbons. So let's go to whatever is attached next. This carbon over here is attached to 3 hydrogens. So that's not doing too well. we go over here, and this was only attached to 2 hydrogens and another carbon. So that's slightly better. And then we come over here, and this one also has 2 hydrogens and another carbon. So these two are still going the exact same. So that means we're competing with these two, but we already know that this group over here is doing worse than these two. So this one is group 4. Alright? Okay, so that's group 4. So we looked at this one. So now we're going to move on over here. So this carbon is attached to 2 hydrogens and an oxygen. Okay? And then this one over here is attached to, it's attached to 3 oxygens. So we know right off the bat that this carbon won, because 3 oxygens versus 1 oxygen and 2 hydrogens, the 3 oxygens are going to win, obviously. So that means this side has higher priority. So this would be 2. And this would be 3. So we're looking at that, we see it, and, oh, well, here. Let's just assume this one was, oops. Okay, you know what? Let's just assume this one was the blacked wedge and this one was the dashed wedge. I didn't realize that they didn't have wedges drawn in, sorry. But even if they had some other wedges drawn, you would use the same process of assigning priority, and the last step would probably be changed based on what it was. But if this was if the hydroxyl group was attached to a solid wedge and the methyl group was attached to a dashed wedge, then this compound, or this Chiral Center, would have a configuration of, well, I'm going from 1 to 2 to 3, and it looks like it's going clockwise, which means it has a configuration of, oops, here, let's do this, has a configuration of R. Okay, sorry, my pen does not want to work today. There you go. Has a configuration of an R. So that's that. That's how you would determine configurations. Okay, so now that we got that down, I know that was long, that took a while. Now we're going to go to that further testing that I talked about earlier. And while we do that, I'm also going to tell you how to differentiate between different types of stereoisomers, which is how to label a compound as achiral, or label them as enantiomers, diastereomers, a meso compound, or identical compounds. And if you kind of read through this, you can see that I kind of put like 2 big differences for each one. I put whether they're chiral or achiral, and then I put what their RNS configurations are like, except for the first one, which you'll understand in a minute. But I just did it that way because I thought the book says a lot of stuff about determining, like distinguishing between enantiomers or diastereomers or Miso Compounds and all. And you can find a lot of stuff online too. But I feel like just because there's so much stuff, so much information going on out there, it's very easy to get confused. So this is how I've understood enantiomers, diastereomers, and Miso Compounds. And this is how I've tackled every problem that I've had in Orgo regarding these topics. So I thought, since this is just like very small tidbits about their differences, they'll be easier to remember and thus easier to apply. So first off, we have an achiral compound, and I didn't mention their chirality because the definition itself says it's achiral. So I went ahead and said its definition instead, which is, or not definition, but how to find it instead, which is if it has a plane of symmetry, which we've done with the letters earlier, like with the letter A and the letter B. So see if you can find a plane of symmetry. And the other thing about the RNS configuration is you only apply that for chiral centers, and for an achiral compound, you can have chiral centers, you may not. So the existence of a chiral center doesn't really do much to whether or not a compound is achiral. So the biggest thing is basically just looking for a plane of symmetry. So the next thing we have is enantiomers. So enantiomers are chiral mirror images of each other, and they have exact opposite RS configurations. So that would make sense because if like you look at yourself in a mirror, you can see that your left side becomes your mirror's right side, and your right side becomes your mirror's left side, right? So the configurations are kind of like the sides of the compound. So since enantiomers are chiral mirror images, their sides get switched, so they have the exact they have the exact opposite RS configurations. Going to diastereomers though, they are still chiral, but they are not mirror images of each other. And their condition is they have the same configuration for one center and the opposite configuration for another. So again, which also makes sense because if they had the exact opposite, then they would become enantiomers. And if they had the exact same, then they would become identical compounds, which we'll talk about in a minute. So they have to be something in between. So that's why they have partial same and partially different. So those are diastereomers, and then we go to meso compounds. Meso compounds are achiral with two or more identically substituted chiral centers, and they have an equal number of R and S configurations. So I included this little bit here because that kind of gives you a way of identifying meso compounds without having to do the R and S configuration. But I would suggest that you do the R and S configuration thing as well, just to kind of be sure that what the answer that you're writing down is right. But yeah, so identically substituted means that all the groups that are around it are the same. So for meso compounds, I have a couple of examples over here. So again, you can say that it's achiral because it has a plane of symmetry. So if you can like draw a line through right here, you can see that this half of the molecule is the exact same as this half of the molecule. And you could actually do the R and S configuration, and they indeed do have one R and one S configuration. But what you could also do is you can see that you can look at their substituents of the chiral center. So there's chiral center 1 and chiral center 2. And you can see that they have the same substituents. They have an alcohol group, a hydrogen, a methyl group, and one other weird long chain that has a alcohol group attached to it. So long chain with alcohol, long chain with alcohol. So yeah, they're identically substituted. They're achiral, and you can go further and test the RNS thing, and I did check them. They do have the exact same number of RS configurations. And so this one's a meso compound. And the reason that having equal number of R and S configurations kind of works is because meso compounds are optically inactive. And if you remember from what I said earlier, the RS configuration kind of determines the properties of some compounds, like optical activity. So for something to be optically inactive, it either does not have chiral centers or it has chiral centers that cancel each other out. So the R's and S's cancel each other out. So, and it's like a known fact that meso compounds are optically inactive. So that's something that you'll need to memorize at some point. So if you think about it, meso compounds can only be optically inactive if they don't have any chiral centers, which wouldn't make them meso compounds. If they didn't have any chiral centers, they would be achiral. So the other option would be if they had equal number of R and S, because the R's and S would cancel each other out. So yeah, that's why that would make sense. And then for identical compounds, before that, this was another example for a meso compound. Again, you can draw a line down over here, and then you can see it has, these are the two chiral centers. they have the groups methyl group, a hydrogen that they're not showing, and then kind of bond to each other basically, and then a bond that's coming out, or a group that's coming out. So this is also a meso compound. Moving on, this is the next one, and the last one is identical compounds. So for identical compounds, chirality is irrelevant because you're basically looking at the same compound. So like you're comparing the same compound with itself. So it doesn't matter if it's chiral or achiral, because if identical compound A is chiral, then identical compound B is also going to be chiral, and same if they're achiral. So it doesn't really matter if they're chiral or achiral. What you can do to test if two compounds are identical is to look at their RS configurations. So if they're identical compounds, if they're the exact same compounds, then they will have the exact same RS configurations. So that's the condition over here. If they're identical, they have the same RS configurations. So I have an example over here. Let me see if I can zoom this in so that that little thing isn't covering it up anymore. Oops. Okay, there you go. So in this picture over here, we have all the stereoisomers of this compound drawn out. So there's 4 stereoisomers. And you can tell that they're stereoisomers because they have different combinations of wedges. So this one has 2 forward pointing wedges, 2 backward pointing wedges. 1 forward and 1 backward, where the forward is the hydroxyl group, and then 1 backward, 1 forward, where the forward is the bromine group. So they're all different. And we said enantiomers are chiral mirror images that have the exact opposite RNS configurations. So I'm not gonna draw the whole thing out because, as you can see, it's taking a really long time for me to draw this, but I can like talk it through. Oh yeah, I still have to. Let me go to, oops, wrong one. Let's do blue. So, oops. Oh no. I'm gonna draw a dashed line like that. That's not how you draw it, but this is how I'm gonna draw it right now. So, oops. Imagine that there is a hydrogen right here. Give me 1 second, sorry. Come on. Let's do that. And I'm gonna put that right there. Sorry guys. There. Okay, so that's why I'm not gonna attempt this again. I'm only gonna do one, but I'm gonna write the answers for the other ones and you can check them. Or you could just take a minute right now, pause this video, and try to figure out the configuration of this Chiral Center and this Chiral Center, and check it with what I'm gonna write right now in like 5 seconds. Okay, so I got that the first priority is over here, second one's over here, and third one's over there, and then again the hydrogen is fourth one. So it would be going this way, so that's an R. So let me write an R. Dang, this thing does not want to draw an R today. Fine. There. So that's an R, and you can go ahead and do this one too, but this is an S. So go ahead and do that for all of them. And you can see that this is an S. Oops. well, this is an S, this is an R, and you can see that they're exact opposites, which is why these two are enantiomers. And then if you go over here, this one is an R, and this one's also an R. So this one would be an S and an S, which is why these two are enantiomers. And then you could then compare everything else to each other, and you would see that there's one the same and one's different. So everything else is diastereomers. So for this one, let's see. Just write it. Come on. There. For these two, this one is an S, and this one, the bottom one's actually an R. Or sorry, the bottom one's an S too. Sorry. So it's S. Oops. On both sides. So it's same for one and different for the other. So they're diastereomers. And then the same applies to all of these. So that one, and that one. So that's why all of these are diastereomers, and then just these two are enantiomers. Okay. Whew. Okay, that was a struggle to draw. But we're over. We got through that. So glad we got through that. So, hopefully this made sense, and hopefully you guys learned something from this. And I do have a link in the description that has more practice and explanations, but I want to say it's more specifically focused on achiral and meso compounds, and that is because even though learning how to differentiate enantiomers and diastereomers is also hard, you can like practice it for a while and get it, but for me, it took me a lot longer for me to like understand meso compounds and identify them, because I mean, I don't really know, it was just hard for me. And if you guys are also like me, then I have a link in the description from another YouTube video that I found just through like normal searching, and the guy from that video actually does a really good job of telling how to differentiate between a chiral and an achiral molecule, and an achiral that's just plain achiral, and an achiral that's achiral and meso. And there's also like a little exercise at the end that he does with like 6 different compounds, and it's like really good practice. I thought it was really helpful. So if you guys just want to look at more practice, or if you're still a little confused, or maybe I confused you a little, I'm sorry if I did, then you can just go to that video and kind of get everything cleared up some more, okay? So that was all I had for today. Thank you for watching. If you have more questions, please contact your professor or come visit us in the Math Science Center, and we'd be happy to help. So yeah, thank you.